Hello everyone, today we're back again on AtCoder. I haven't been posting in a while anything on YouTube because we were doing a research paper and now that it is submitted for review, I have again some time to code in these competitions. We're here on AtCoder as usual, so yeah, we're going to have some fun. Nothing special. I'm sorry again for not posting in a while, but I promise I will be back. Okay, so let's go. Okay, Takashi has likes full moons. Today, day one, first day on or after today, on which he can see a full moon is M days. After that, he can see it every P day. So M plus P, so on. Find number of days between 1 and M. Okay, so this is the M is just an offset, and then P is so it is N, M, and P. N N minus M plus 1 divided by P. I think that's the minus M is like, wait, on each 5 days, stay the 3 days, so 3, 8, and 13. Is that well? Plus 1 is 3, 10. Plus 2 maybe. No, it's not. It can be plus B minus 1. This is a little bit different, I think, but there are n rectangular sheets spread out on the coordinate. Each side of the rectangular covered is parallel to the x and y, specifically covers some region, but as be the area covered by one or more sheets. We've proven that integer print s. So this is just A gets accepted. So this is just because this is an area of a union of rectangles, but you don't need to call it as a union of rectangles. What you can do is just make some matrix from 100 by 100 that is like visited or something. I don't know how I call that. 100 by 100 or 110 just for the, because it goes from. So yeah, you can see that I haven't called it for a while. This is ABCD. Then from A to B. Okay, yes. From C to D. Wow, I really haven't called it for in a while. Visited at KL is true. and KL is true from A to B, from C to D, right? Why is this the case? If visited is of course if visited is one, what the A C my being so I don't know what's going on. This is good. Okay. He's playing and day train trip. For each day he can pay the regular fare or use one day pass. The regular fare for the day I the trip is FI. On the other hand, the batch of D one-day passes is sold for P yen. You can buy as many passes as you want, but only in units of D. Each pass, each purchase pass can be used on any day, and it's fine to have some leftover. Find the minimum possible cost of the enter. So the cost is first the sum of all of these, and then after paying something with after getting D, I will eliminate the most expensive ones. So because that's optimal. NDP So here there's, and then we can pay it in pay here if I divides P, if I divides what was D, right? Pay plus equal P, and then here there's like a sum is AI, and then answer is minimum of the answer and the sum, something like this could be. Sum plus pay, of course. Okay. D. You're given a weighted undirected complete graph with n vertices. Weighted undirected, okay, complete. When choosing some number of edges under the following condition, find the maximum possible weight, total weight of the endpoints of the are pairwise endpoints of the chosen edges. So you want to find a maximum independent, not a maximum independent. Yeah, I want to find the maximum matching uh, under this, yes. So let me just close down the door. So this is just just for every subset of the edges, which no, actually there are 16 squared these things, which is 128, right? So you want for the maximum possible total weight of the chosen edges. There are there's 128 edges. Okay, so you have like a matrix, right? And then you want to pick a no. You want to pick in the matrix some permutation, right? But 16 factorial is a lot. When choosing some edges, maximum possible total. So for each endpoint, there is an edge that is chosen. I will choose. Backtracking can't work. So this is an NP. So 16. Okay, 2 to the 16 is what? This man. Three to the 6. Is it just like a burp or something? No? This is wait, how is it represented? Yeah, so this is 1 through n, and then 2, 3. Also, this is 1 through n minus 1, and then 2 through n. This is how it is represented. Okay, so let's think about this. How we brute force this? There for each edge, you could have it either in the set or outside the set, right? But you need to. There are a lot of edges, or n squared edges, divided by 2 or something. So, but each edge will constrain some other edge. But you have to kind of do some. If you choose this edge, then what other edges could you choose? General weighted maximum matching is. I will need to remember my algorithms. General unweighted. Is this the thing? And then general weighted is possible, but some. Yeah. General unweighted is the boss mounter. Okay, so 16. But brute force over what? We pick the. Insert the edges, then we go. Backtracking? No, backtracking is too much, right? I'm not sure, actually, to be honest. Backtracking is too much. Or is it? I'm not. See another way of. About some divide and conquer, so. Now, 2 to the 64 is still a lot. Backtrack, just backtrack. I don't see another way. Go into. Sort them and then. Or does it even matter? So, there are only 16 times 16 divided by 2. So this is how many edges there are, and then or choose to do whatever. 128 edges, let's assume, and then there are, from all of these edges we choose, so this is like this, 6, choose what is now going on? Come on, Wolf, the complexity, I want to calculate the complexity of my backtrack. So there's 128, and then from 128 we choose, from all these edges we all need to choose like 16. How many combinations are there of this happening? A lot. They're all positive weighted, so when they're all positively weighted, then can I do something more greedy? Take the word. There's a lot. Let's go read. You're given a sequence of positive integers. Find the number of triples of positive integers that satisfy the following condition. These are equal. These are not equal. And all of them are up 10. Okay, this is one. Okay, so we fix J, and then we want to say that J, we want to say how many are equal on this side and how many are equal on this side. Right? So, okay, so how many are equal to this side, how many are equal and different from J? So how do you do this? From this side you keep some, this is the sum of, what is it exactly? It's the sum of the products of the counts from, so if I have like a secretary, so the, when I add here something to the second tree, so because this is equal to the sum of whatever on the left side of some number, some AI, times whatever the right side of this AI is equal, then this here close thing, then minus this AJ here, the left AJ. So this is actually just saying, yeah, minus left AJ times right AJ. And can we do this in a segment tree? So from the left, if I have a node inside the segment tree and I increase the left, then this node then should give me information, and I just query at the top and I query at this node. This is just the easiest way to do that. Like having like one segment treated. Yeah, let's call it like this. It doesn't matter. Yeah. So seg tree. So in the node, I want to have two things. I want to have the value of the node, and I want to have whatever it is on the right and whatever it is on the left and on the right. Okay, power. So this here is just 4 times n. Just not fix this because it will sometimes overflow. Okay. And here on the merge of the node, it is value. It is left times right, and then plus this dot value plus other dot value. Right, so value plus other dot value, and this is 0 and 0. Okay, and then just simply do my dp back and forth trick. No, segment tree. This is from up to n plus 10 or something like this. And then tree dot put. And okay, so what we want here is, instead of v, what we want is like to increase left and to increase right. And then this is left plus equal left, and same index right plus equal right. Okay, and now here is like left and right. So this is just that. That's brilliant. Now put me into the a of I. Then this is the right side, so I'm not going to increase left, I'm going to increase only right. Okay, and then I will, so here I will delete from the, so this is this, I will delete that, then tree. What is this? Tree put a of I, and I will delete the right side. Tree put a of I minus 1, I will add to the left side. Tree ask LR for the whole range, 0 to n plus 1. So this is ask for the whole range, and then minus is tree ask LR from AI. This is the AI and AI plus 1. So this is just only this node, right? That's correct. Yeah. So res dot value minus dot value is whatever and what do we want to find? The maximum? Find the number of triples. Yeah, the answer is this. So okay, so that's not correct, but let's left times right plus value. Okay. Here we add all of these to the right side. We then negate what was on the right side in my current position of what was in the left side in my current position. Oh, it was, we added on the left side was prior. And then we ask for the whole tree. And also we ask for whatever I am here, because this cannot be, this should be equal, but this should not be equal. This is whatever I'm asking here, right? And AI goes top time. Okay, let's see just what are the triples. 1, 2, 3. So there's just 1, 2, 3, this triple, then there's this 2, 2, 3, and 5, this triple. This should be the case. I don't see how. The left side, we added to the left side. Oh, yeah, the right side we added. And then the value is, of course, the value has to be updated. Sec index dot value is sec index dot left times sec index dot right. This should be updated as well. We have 2 for some reason. Why we have 2 here? So left, right, we update the value. Yeah, not exactly. We just want here value, I think. Yeah, that should be the case. Okay, we send this. Okay, so F, what is F? There's some octopus-shaped robot with n treasures on a number line. The ith treasure is located at xi. The robot has 1 head and n legs. That's a length of li. So there are some locations of the treasures, and then the robot has 1 head and n lengths. The ith length has, so there's some intervals. Find the number of integers k such that the robot can grab all n treasures as follows. Place the head at coordinate k. Repeat the following for all of these. If there is a treasure that has not been grabbed within a distance of li from the head that is coordinate satisfying these conditions, choose one such treasure and grab it. Find the number of integers. Okay. This is some kind of a DP or some problem. Okay, we get E accepted. So let me just see where we are on the standings here. So yeah, D we have to solve, and then F, a typical path problem G. Is of course non-trivial problem. You're given a simple connected undirected graph, the vertices and edges also given 4 distinct vertices, ABC, also given 3 distinct vertices, A, B, and C. Determine if there is a simple path connecting vertices A and C via vertex B. There's a graph, and there's A, B, and C. Determine if there is a simple path connecting vertices A and C via vertex B. So if there is a path connecting A, means that B, yeah, that's not an easy problem, even though it's just one liner. But from B, A and C have to the shortest path from B to A and C. No, it doesn't mean to be the shortest path. It could be any path. There needs to be some path just that don't have any intersection between them. This is not a simple problem. Okay, so F and D. So let's just focus on D first. Do we brute force or what? We are supposed to brute force something, but what are we supposed to brute force? Edge connecting vertices I and J. So there are these edges that, so there's this full graph. Let's just draw a bigger graph. And then you're supposed to choose some maximum matching. You can't brute force over the edges because there are 16 times 16 over 2 edges. It's 15. But most of these are not touchable, so they are is it like this? So 16 choose 2, and then from all of these edges you don't choose 16, you choose 8. Choose 2, and then you choose 8 from all of these. Yeah, okay, I'm gonna brute force it like this. So edges push back ij, and the weight is this. Then we want to sort edges by weight. the maximum weight first, right? And then I'm at edge 0. What edge am I? And then how much is the cost till now? Starting at this edge, and then to the edges dot size. Also, I need to have like some matrix that is like visited. So this is edges at J. If it's not visited at U, and then it's not visited at V, then DFS in the next edge, then answer is the max of answer, and the DFS in the next edge with the cost plus weight upon added. So answer is the cost till here. Wait, does it have to be like a full maximum possible return answer cost plus this edge from the next edge, and then plus the weight of my edge here. Also visited at U is true, visited at V is true, and then we revert this back to false. And this is that. Okay, everything sounds fine, but it's not fine. Let me just see here. Oh, I think that's... Wait, what? How fast is it? 2 point something seconds. Wait, sorting that should not influence any of this, right? I mean, random shuffling would better do it, right? Random shuffle. Um, 2.5 seconds. Maybe you should sort it, but not by weight, but by like V vertex or something like that. What about this? Okay, I think this should be fine. We'll see. Yeah, it gets just accepted under the limit, okay. There is an octopus-shaped robot, so there is some length here, and then the length should, so you should, if you choose this coordinate, how is this affecting these lengths? And this is, so there are equal number of, so there are some fixed coordinates, and for a coordinate k, there are some legs that extend like this. And we want to see if how many, if they can grab all end treasures. Let's say like this, they won't be able to grab because this treasure won't. But if I move it maybe a little bit further, let's say it's just like this, maybe if I move it a little bit further to this side, and this point kind of can grab this treasure as well. So this point grabs this treasure, this flag grabs this treasure as well. This catches also something. And there could is there a monotonicity in this function? So is there like not a monotonicity but like some interval where this satisfies and then doesn't satisfy? So let's say our interval is from like to here, set it here only satisfies and then it doesn't satisfy, that's it. This is some kind of a, like an IOI type of problem because you have this it's pretty straightforward problem, but pretty straightforward definition, but it's not implementationally straightforward. Okay, so this is F, and then we have G. They're both equally worthy problems, F and G. But G is a graph problem, which I like more. So if you imagine in a graph, there would be A, B, and there are these 3 points, and a simple path won't have any intersection between these two things. This is undirected graph, right? Yeah. Simple connected on there. If there is an intersection somewhere, it means that there. So if there is some intersection like this, means that there here is a bridge between this here and this here. Because if there wasn't a bridge, I would just take the other route, right? So here it seems like bridges is something that we don't want to do. So for each like bridge, we want to say like really quickly maybe on which side does it like. Otherwise, also, yeah. Also, what happens if there is something like an articulation point? Maybe there's something like this. And then, like, let's say that, so this is an articulation point, right? And then if I go, I will end up in this. This is no longer a simple path. If I have somewhere other articulation point, some other articulation point here, I don't care about this point. If I have something like this. For each articulation point and for each bridge, I want to say where on this side. But then can there be a case where you have something like if so we want to know if we delete this point, is it so that this becomes one component and this becomes another? Or maybe more components. We want to quickly know for each articulation point, is B connected to A or not? And C. Even if there are articulation points somewhere, there should be a path or maybe something with like biconnected. Biconnected components. Something which you have two paths to come to these points. Each of these points will have like two paths to come to there. So biconnected component is maximum biconnected of any connect. The blocks are attached to vertices and articulation points. Relevant structures, algorithm. Wait. Biconnected subgraph. Non-separable, meaning that if any vertex were to be removed, the graph will connect remain. Therefore, a biconnected graph has no articulation vertices. Yeah, that means that if B, C, and A are in the same biconnected graph, subgraph, it means that you can access B, you can access all of this, but C and A could be. Is it possible that C and A could be something like this, though? It is possible, right? B would be connected to A in. So this is possible as well. It could have articulation points here, but still there's a simple path because there's no intersection between. Mm-hmm. This maybe is a special case somehow. We treat this as a special case. We treat that. The symmetry from the B point of view allows maybe for if I fix one path and then the other. What if I go like a DFS? So like I go here, let's say I touch A first. I visit A. Then I go somewhere and I visit C. If then I can visit, so I visit C, then I can visit, then somehow I visit B. What if I visit somewhere? So I go B, A, let's to prove something here, probably. So, okay, so my first lemma is that definitely if A, B, and C are in the same biconnected component, answer is yes, there is this path. We need to print it? No, we just answer is yes. That's my first one. What if B and what if they're all in different biconnected? So if they're all in different biconnected components, is this kind of a case here that there has to exist a simple path that okay, what if A and B are in the same biconnected component? What does that mean? What does that mean? Does it mean something? No, it doesn't mean. If B and C are in different biconnected, if B and C are different biconnected components, means that there is an articulation point somewhere. And this articulation point can be then thought of as being C. This articulation point can be thought of as being C, the closest articulation point to B. Because this here path has to be. Does it have to be? No, it doesn't have to be. So there could be like another path here, and then there could be like a path like this. But certainly we can compress this into one node. Certainly we can compress like a biconnect component into one node. So that's like lemma tool. We can compress biconnected components. Connected components. Because we can always find, so we can compress biconnected components. But how does that help? It doesn't help a lot. The path of I vertex Z for a simple path connecting X and Y is some distinct. There's no edge G connecting. There's an edge G, yeah. Simple path set to be Y vertex is vertex Z somewhere. So yeah, so there has to be a sequence of these vertices such that all of them are distinct. This is what it means that no articulation points can be there. I mean, yeah, there can be articulation points, but we don't care about articulation points that go off. Okay, so let's consider all the cases. Consider that they're all in different bi-connected components. If they're all in different bi-connected components, so there's some bi-connected component here, there's some maybe here, there's some maybe here, maybe here, maybe there's some. What does that tell us? Just the articulation points are very powerful here, tools. There's something, so consider one vertex. This one vertex can be in the path from B to C, can be in the path from A to B or whatever. Doesn't matter, but vertices which are like not in a path, not between two, don't have like these edges, we don't care about them. We can just delete them. So like let's assume that each vertex has two edges going out, one in some direction and one in some other direction or multiple directions. If there's like something. Any idea here? Except the background components oh. The graph is too big to run anything on it. Except like a DFS. And it's undirected, which means there's no luck in simplifying the problem any further. This is the only case where we have the answer. A and C What if they're connected? If they're connected, it doesn't really matter. They will be connected always, but like if there's a simple path thing. So okay, if I start at A, let's say, or here, let's say, and then I go B, and then I end up going into C with like the DFS, then there is certainly a path. But what happens if I like go to C first? Then I can go maybe to B quite directly from there. And then you want to go if there it has to go back to a node which is not visited from A. It has to visit A again in order to be a successful simple path. Because if it visits any node that is here in this region, well, no, actually, yeah, actually you could visit like that and still be a simple path there. So when will that never happen? So if I assume that the answer is yes all the time, when wouldn't be a yes? It wouldn't be yes if B has one neighbor, of course. That wouldn't be yes, of course. Mm, wouldn't be yes if and only if the something with bridges and articulation, please. They're so they're not in the same background component. Or does B have to be in a back? No. So there's DFS. I go with the DFS, and then I so yeah. I started B. I go down. I will eventually reach A. I must reach A. One of these nodes, A or C, whatever, doesn't matter. And then if I somehow from A reach C, I have to know that I need to reach B from there. But what if I have something like this? What happens? If I don't reach B from there, in any of these nodes, I don't reach B, then it means that there is some articulation point between this here. If I don't reach B, so I have to reach A. So I DFS from B has to reach A, and then has to reach C, then has to reach B again. Or it has to reach C, then A, and then however you look it. But what, or there goes A, and then it kind of returns back, and then from here goes to some other path, and then goes to C. Or either this, DFS B, then reaches A, then returns to B, and then goes to C. Or reaches C, then goes to B, then goes to A. So either in this or in this situation. So A and C, because of the symmetry, I will kind of flip and do the DFS twice, probably. But yeah, so I mean, I think it's something like that, but I'm not sure. So this is Jason's matrix, then that, then U, then the parent. Oh, of course, here, here, oh, that's fine. So, okay, so for each of the Jason here, there's like this. So visited A, visited C is false. So if U is equal to A, then this A is true. If U is equal to C, this C is true. If U is equal to A, this A is false. Yeah, U is equal to C, this C is false. So because we already know that we first visited B, then we go down here, we visit something like first we visit A, then if this the parent want to continue here, so Okay, so I will here void, and then I will say bool answer here is false. And here I will just do this. So I'll start at B, then swap it, then start at B again. Then at the end is the answer. Yes. Then what we want is to say visited at C is okay. So there are this case where I visit first A, then I visit C, then back to V. So if so there's like visited, so I don't quite need this. I can just say, yeah, actually I need this. Visited is something, and then this is visited fill in visited and swap it, and then do this again. Okay, and then visited u is true. If visited u, then now this is we already have visit, but if it's first visited at A, then it is visited at C. But what if there was something like this? Then you go to some node, you visit A, then you visit C, and this node here. But then you will go here. Oh no. Then you will, let's say that there's like something like this. And you will go here, and you will return back, then you will go here. So essentially you visited B, then A, then C, and then A, and then you returned back to A, and then you visited to B. Because there's some this doesn't quite work. Is it provable that one of these paths will be the shortest path? Can this be actually provable? So can you prove that? So like, is it provable? So conjecture that either in the solution either a BA or PC is the shortest path from A to B and B to C, respective. So either this is the shortest or this is the shortest. Because so let's see. Can you make a case where this is not true? There's A and C and B, and then you want to. So the shortest path is like this, and let's say the shortest path is something like this. One of these will certainly be shortest, I think. One of these will certainly be shortest. How can you make it not do both? So like, let's say this is a longer path and this is then a longer path. And one of these I can compress this to a shorter path. I think this is a correct conjecture, but I'm not sure. So if I find what is the shortest path from A to B, but there could be multiple shortest paths. And what is the shortest path from B to C? Then I immediately like take off one of these paths and then I try to find a way to B or C or something else. Something like this. I will try it out. I will try it out here. So the shortest path, there has to be like a B test or something here. So B and target. If distance V is greater than or inverse V is greater than distance at t plus 1, distance V is t plus 1, parent V is t, so this is vector and parent, right, and then parent at V equals t. Okay, that should be okay. So okay, while u is not -1, so the target, while t is not -1, t is parent t. Turn path. Okay, so this is fine. Okay, So first, what we're gonna do is we're going to path is BFS at B to A, and then path is BFS at B to C, right? And then I want to the path that it takes to the like the shortest is something like this, and then DFS from B to C to the target to parent is -1C, and then here to A, and then the DFS here this here in parent we say visited at t equals true, visited at t equals true, so we don't need to return anything here, we just make that. So make them visited, so you can't visit them again. And then we have the target. This. Okay. The oops. From 2 and 3, which means that first you have to go through 3 and then 2, and then the shortest path is from 1 to 3 like that, and then from if it's visited at V or V if you want to continue. T is equal to parent of D, well D is -1, and the distance parent distance is bigger than distance, but distance of B. So when it's through A, it visits only one, then also A is visited, right? B is what? 2. This is visited from 1 to 2. So from 1 to 2 is visited. And then from what? Oh no, B is here. From 3 to 1 is visited, but 2 has to be visited as well. B to A, 1 and 2. 1 and 2 are visited. So and then B to A 1. Start at B. Wait, what's going on? We start at B, which is 3, and then we go to 2, and then we go to of course Q that push V. Where's what? 0, 1, 2. 1 and 2. Okay. All visit the target here has to be here for some. You see that passes, so it just keeps wrong cancel. That's wrong cancel. V equals to the target, but V is what sent from B to C. From B, it's 3, and then you cannot send it. From wrong cancers. The target here is sent, and then B is sent as well, right? Right. And then when it's visited, B or the target is visited, then it's no. But we're missing something here. I'm trying to think of every possibilities, but No. I think it's the shortest path. Like, I think. Let me just read the tutorial. Maximum flow. Wait, you just push max flow? I mean, yeah, but isn't the graph just too big? What's the Dinitz time complexity? Isn't there a factor some Dinitz? Yeah, because you have this limit on the edges in the sink. Okay, we could have solved that one. Okay, doesn't matter. Wait. So yeah, the problems we can go through them one more time, but they're not that interesting. I mean, they're fine. They're fine. They're fine. So okay, so problem A, we were just wanting to count this how many times we see the full moon, and the equation for this is n minus n plus 1 because we want to decrease first by m because it's some kind of an offset. The first moon is on day m, and then we after that you see the moon every p days. So when we decrease this, we want to divide by p, but we want to seal that. So to seal that is just plus p minus 1. And this kind of cancels out and just n minus n plus p. But that's a mathematical just formula. Here there's the union of rectangles, the overlapping sheets. The union of rectangles is a very well-known segment tree problem, but here you don't need to do any segment trees. You just want to iterate from A to B and C to D. So just have a matrix where this 100 by 100, and then you just flip the bits that are on. After that, you want to count how many of these bits are on in this matrix. I mean, booleans. So it's a pretty straightforward problem, but it's an interesting technique to know, to brute force. Just let's go. C was straightforward, just a mathematical problem. You were given these costs at this dive day on this trip costs FIEN, but then you can buy a batch of D passes, which is sold for PN at always like this price. And we want to somehow balance this out. And the trick here is just to first sum up all of them, how much it will cost you if you buy them all as like FIN. But then you want also to you want to maybe some buy some batches of PN. Maybe that's more worth it, right? And what you want to do is you sum up all of them and then you sort them in reverse order. So you sort them from the highest to the lowest because you want to exchange these highest things first for like this D highest things first for P, and then the next D highest things, and then the next D highest things, and so forth, so forth. So every time I divides D, we want to pay for a batch of D things, and the next D things that we paid for, we're just going to subtract them from our sum, and the answer will be the minimum of whatever the answer we had, and the sum. So this is the sum of the remaining things plus what we have paid already to just subtract these already high value items. And this is what this formula is, just simple mathematics. Now D, I don't know what is the editorial for D, but what I did is, so apparently DP, apparently DP is the editorial, but what I did is just brute forced. So I sort the edges first by V's, by some from either U and V, but I sort them by V, whatever, doesn't really matter. This allows me to have a concrete deterministic sort, deterministic, how do you say this? Deterministic order of the edges, So the order is very important because after that I initialize DFS and I just brute force. And what I do is I go from whatever edge I have. So if my edges are there are a lot of edges actually. So this is a full graph here, and there's a lot of these edges. And then I sort all of these edges have three components. So I sort them by U, V, and W. So I sort them by V. So this is like, okay, this edge, let's say, goes from 1 to 2. So it goes 1, 2, and has some value, let's say 10. Then there's some other edge that goes from 1 to 3 and has some value of 20 or whatever. It doesn't matter, and all these edges. And now, if each edge would be represented as some blob or something, all of them are sorted. What I'm actually doing, and what is possible with the fast C++, of course, what it is possible, it's, so I'm at some edge here, I have something, I have done some other things here. So I have this edge chosen, and then I try to choose from these edges some edge. So let's say I try first to choose this edge, but there could be an overlap with some chosen other edge here. And then, okay, if I can't choose this edge, then I just go here. I skip it. And then I try to choose this edge. And let's say I can choose this edge next. Then I add it to the count, and I now move this DFS over to here, and I have this chosen edge, and I try all the other edges. And Now the idea is this is just a backtracking brute force approach, but it works because C++ is a fast language, um, and frankly, I didn't see any DP here approach, but yeah. So I go to the next edge, start at the next edge, and then I add the cost of the current edge if this current edge, both of these vertices are not visited, and I calculated that there are this many edges. There are 840 billion combinations what I need to try out, and this is fast enough to pass because this is it's not going very deep, and this is very fast. It could be optimized. So E was the problem. E was the problem behind like with a segment tree. So I don't know if you could solve this problem anywhere, but E was my favorite problem of them all. Not because it's like really small, but because it's not because it's really small, but it's clever in a way how I solved it. So if I have some numbers, and these numbers are somehow like this, then I have for each triple I have I, j, and k, right? For each triple, yeah. So I fix j, I iterate over all possible j's, so all possible j's, and then I try to find how many on the, so if j is something here, I try to find on the left side how many of them can be combined with how many of the right side. So if twos, how many twos on the left side can be combined with how many twos on the right side, and how many ones on the left side, how many ones on the right. But there could, if here it's 2, you cannot have this 2 here. So I take a look at all of them, including this equality, but then I subtract only the number that is equal to this number, to my j here. And the trick here into doing this really incredibly fast is a technique called move by one, or DP left right. I'm not sure how it's actually called, but I think I call it move by one or something. But it's very, very simple. And first you have two data structures. But now I solve it with one data structure, because this is where the problem actually, this is why I like the problem, because I combine these two data structures into one. So you have usually you have a left data structure and a right data structure, and all of these elements are in my left data structure, all of these elements are in my right data structure. And when I move by one, so when I move this element over here, I delete this from the right data structure and I add this to the left data structure. And now the left data structure comes like this and the right data structure comes like this. And then you query out in these two data structures some interesting idea. Maybe something from the one data structure times something from the other data structure, then you sum up something like that. But what I actually did is I had one segment tree where, so if you know like a segment tree, how it works, of course, I won't explain here in the detail, but in each of my nodes, I had each of my nodes represented how many ones I have, how many twos I have, how many threes I have, how many fours I have. And then each of the nodes had left and right how many on the left side once I had and how many on the right side once I had. And this is equal for each node. Left, right, left, right, left, right, and left, right. Then let's say here as an example. So here, if this is my example, remember this is on my left side. So remember, I'm here. On my left side, I have 1, 1 and 1, 2. So 1, 1 and 1, 2 on my left side. All of the others left are 0. And on the right side, I have 3, 1, and 2. So I have 1 on the right side, 2 on the right side, 3 on the right side, and 0 force. And now my segment tree is essentially multiplying these two and getting a value here, which is 1, and multiplying these two and getting a value here, which is 1. Here is 0, and here is 0. And then summing up all of these values. And it tells me here at the end that I have two pairs, two triples that satisfy this condition, that this is here in the middle, and then there's this one triple which has this 1 and 1, and another triple which has this 2 and 2. If I had one more 2 here, there would be like more triples here, something like that. Because there will be 2 2s, 2 times 1, like that. But now for this simple case, it's like that. But you have to notice that this is 2 as well, and I and J, AI and AJ cannot be equal, so AI is not equal to AJ. And this is what the segment tree is very cool, and then you can query just this node here in the segment tree and say, okay, this node has on my left side 1, and on my right side 1, 2, so it's one value. And this value here I can subtract because I don't want to count this pair. And then here it's counted only one pair, which is one triple. 1, 2, 1. In a case where this here, it would be counted if it was like this here, there will be counted like this. So the answer would add, this would add 3 to the answer. And we won't subtract anything because this 3 would be 0. There's no pair combining these. So this is kind of a cool way to construct a segment tree, sometimes having some data structure inside the segment tree here. So this left and right, keeping these two values, and then propagating the sum up there, and just query out this top value here. Very, very cool. The code is very simple. Only here I had to change the node, of course, and I had to add my custom things to the put function. Is just like update function. It's very, very straightforward. G, yeah, I didn't solve G. It's just max flow, just max flow. So I thought about max flow, but I couldn't come up with. So I didn't know that it would work because the graph is so huge. But what you have is you have 3 nodes that are given A, B, and C. And then you want to find some, and then you're given some graph, whatever, doesn't really matter. But then you want to find, is there a simple path from A to C via B? And you can model this max flow, this as a flow, and say that each edge has a value of 1. And there is a node, let's say sync here, which has 1, 1. And then here there's a node, and here there's a node source, which has 1. So this is T. And then you want to find, then the flow will flow from here to A, and actually to here. There's 2. Okay, whatever. The flow will flow here to A. So the flow will flow somehow here. And then it will flow as well in this direction as well. And this is actually the whole idea, so like just to push max flow. But then it has this time complexity of v plus c squared or something like this. But this is if it's like if the graph is if you're having like a lot of flows and a lot of things here, because the flow is constant limited, somehow you can prove this. But I just would not worry about this problem right now. I will check the proof again later why didn't works. So thank you guys so much for watching. I will upload this video as soon as possible, and I see you in the next one. Thanks.